Good afternoon, dear children. We can continue the lesson gravitation. Last class we have discussed about the laws of gravitation, and also we have learned about escape velocity. Okay, and also we have learned the expression for escape velocity. Listen it. And today's class we can talk about satellites. You know what are satellites? Actually, it is a heavenly body that revolve around a planet in a fixed orbit. Okay, actually satellite is a heavenly object or body which revolves around a planet in a fixed orbit. Okay, there are artificial satellites as well as natural satellite is there. An example for natural satellite, okay, moon is the natural satellite of earth, and lot of artificial satellites are there. For example, Aryabhatta, Sputnik, then InSat, EduSat, these are artificial satellites. Listen to it. And next we have to find an expression for orbital velocity of satellite. Okay, orbital velocity. Orbital velocity of satellite. Then what is meant by actually orbital velocity? Actually, it is the velocity required to put a satellite in its orbit around the Earth. That is actually called the orbital velocity. The velocity required to put the satellites in its orbit around the Earth. That is actually called the orbital velocity. The velocity required to put satellites in its orbit around the Earth. That is actually called the orbital velocity. Also, we can say orbital velocity is the velocity with which the satellites revolving around the Earth. Okay, the velocity with which the satellite that moves around the Earth. That way also we can define what orbital velocity. So orbital velocity is the velocity required to put satellites in its orbit around the Earth. Okay, also we can define orbital velocity as it is the velocity with which a satellite which revolves around the Earth, that is actually called the orbital velocity. Next we have to find an expression for orbital velocity. For that we are considering Earth having mass m. Earth has mass capital M and its radius is capital R with the center at O. Listen to it. Consider Earth whose mass is capital M and its radius is capital R. Then at a height h above its surface, we consider a satellite of mass m which revolves around the Earth with the orbital velocity VO. With the orbital velocity VO, and the orbital radius of the satellite is R plus h. Okay, the orbital radius of the satellite is actually this total distance, that is this much R, then remaining is h. So the total distance is R plus h. Listen to it. Here we are consider the mass of Earth is capital M and its radius is R, and from the Earth's surface, above the Earth's surface at a height h, the satellites which revolve around the Earth with orbital velocity VO and orbital radius of the satellite is actually R plus h. Listen to it. Then according to universal law of gravitation, the force of attraction between the Earth and the satellite, we can write the force of attraction between the Earth and the satellites, that is F is equal to G mm divided by, according to universal law of gravitation, the force of attraction between Earth and the satellite can be written as G mm divided by R square, and here instead of R, actually the distance between the center of Earth and the satellite is R plus h. So it is R plus h the whole square. R plus h the whole square. F is equal to G mm divided by R plus h the whole square. Listen to it. And next, these satellites, in order to revolve around the circular orbit or around the Earth, the satellites require what? Centripetal force. And the centripetal force required by the satellite is given by Fc is equal to, actually the centripetal force is mv square by r. That is the equation for centripetal force, mv square by r. Here the distance is actually r plus h. So we can write mv square divided by r plus h the whole square. That is the mv square by r. So r plus h. Fc is equal to mv square divided by r plus h. That is the centripetal force. Listen it. Here the gravitational force between the earth and the satellite is given by Newton's law of gravitation. That is gmm divided by r plus h the whole square. And the centripetal force recovered by the satellite is actually mv square by r. Here the distance is r plus h. So we can write mv square by r plus h. Listen it. And here the centripetal force recovered by the satellite is given by the gravitational force. So we can equate these two. Okay. The centripetal force recovered by the satellite that is given by, that is provided by the gravitational force of attraction between Earth and the satellites. So we can write mv square by r plus h. mv square divided by r plus h is equal to gmm divided by r plus h the whole square. Gmm divided by r plus h the whole square. Actually here it is the orbital velocity. So we have to write v0 square because the orbital velocity is represented by v0. So we can write mv0 square divided by, or vo square divided by r plus h. Okay, and this mm cancel, and on r plus h and on r plus h cancel, and so we can write v0 square is equal to, what is v0 square actually? Gm divided by r plus h. v0 square equal to gm divided by r plus h. From this v0 is equal to root of gm divided by r plus h. Okay, that is expression for orbital velocity. Vo is equal to root of gm divided by r plus h. Root of gm divided by r plus h. But we know the expression for acceleration due to gravity, g is equal to gm by r square. That we have learned. From it, when cross multiplying this, we got gm is equal to gr square. Gm is equal to what? Gr square. So instead of gm, we can write a gr square. Okay. Here Vo is equal to, we got root of 2 gm by r. Okay. Then but we know the value of gm as root of gr square. Root of gr square. So Vo can be written as square root of gr square divided by r plus h. Gr square divided by r plus h. Suppose if the satellite is very close to Earth's surface, then height h is equal to 0. Suppose if the satellite is revolving very close to the surface of Earth, then h can be taken as 0. So Vo is equal to square root of gr square by this h0, then r, then we got root of gr. Okay, this is another expression for orbital velocity. So we have two relations of our orbital velocity. Vo is equal to root 2 gm by r plus h, or Vo equal to root of gr. Vo is equal to root of gr. Okay, then we know the value of acceleration due to gravity, 9.8 meter per second square, and about the radius of Earth is actually 6.4 into 10 power 6. By substituting this, we will get the orbital velocity as actually 7.9 kilometer per second. Orbital velocity, the value of orbital velocity is actually 7.9 kilometer per second. 7.9 kilometer per second. That is the expression for that is the value of actually orbital velocity. Okay, and here I'll repeat once again. See, here we consider Earth has mass capital M and its radius is r. Then we are considering a satellite of mass m that revolves around the Earth at a height of h from the surface of Earth. And Vo, that represents the orbital velocity of satellite, and the orbital radius of the satellite is actually r plus h. Listen to it. Then according to Newton's law of gravitation, we can write the gravitational force between the Earth and the satellite. That is F equal to gmm divided by r plus h the whole square. Then the centripetal force recovered by the satellite is given by mv0 square divided by r plus h. Okay, and here the centripetal force required by the satellite is given by the gravitational force. So we can equate these two forces. So mvo square by r plus h is equal to gmm divided by r plus h the whole square. Then mm cancel and r plus h cancel, and the remaining is vo is equal to root of gr square divided by r plus h. Sorry, V0 square equal to Gm divided by R plus H. From this VO is equal to root of Gm divided by R plus H. Okay, VO equal to root of Gm divided by R plus H. But instead of Gm, we can write Gr square. So we got VO equal to root of Gr square divided by R plus H. Listen to it. Suppose if the satellite is very close to Earth's surface, then height h can be taken as 0. So u equal to root of gr square by r. Listen to it. So r cancel and we got the expression for orbital velocity of root gr. We got the expression for orbital velocity as root of gr, and substitute the value of g as 9.8 meter per second square, and the radius of Earth is 6.4 into 10 power 6 meter. Then we got the value of value of orbital velocity as 7.9 kilometer per second. 7.9 kilometer per second. That is about orbital velocity. Next, the relation between escape velocity and orbital velocity. Okay, what is the relation between escape velocity and orbital velocity? You know the expression for escape velocity, v is equal to root 2 gr. Okay, and the expression for orbital velocity is VO is equal to root of gr. Okay, we have the expression for escape velocity root of 2 gr, and the expression for orbital velocity is root gr. Then we can take V by VO is equal to root 2 gr divided by root gr. Listen to it. And this root gr cancel and we got root 2. So escape velocity V is equal to root 2 v0. We got escape velocity v is equal to root 2 v0. Okay, that is the relation between escape velocity and orbital velocity. That is, escape velocity is root 2 times the orbital velocity. Escape velocity is root 2 times the orbital velocity. Okay, we have the relation escape velocity v is equal to root 2 gr. That thing you know. Then the orbital velocity is root of gr. Then taking the ratio, that is V divided by VO, that is equal to root 2 gr divided by root gr. Root gr cancel and remaining is root 2. So we got V by VO equal to root 2, or V is equal to root 2 V0. That is, the escape velocity is root 2 times the orbital velocity. Escape velocity is equal to root 2 times the orbital velocity. That is the relation between escape velocity and orbital velocity. The next about the time period of satellite. The time period of satellite. Actually, what is time period? The time taken by the satellite to revolve around the Earth or a planet. That is actually called a time period. Okay, the time taken by the satellite to revolve around a planet or Earth. That is actually the time period of satellite. Next, we have to find an expression for time period of satellite. Okay, for that, you know, time period can be written as orbital. You know what is time period actually? The distance by speed. Okay, suppose if the satellite that revolves around the Earth in this circular orbit, actually the distance is, you know, r plus h. Here is the satellite. Okay, so the time period equal to the distance travelled by the satellite, that divided by the orbital velocity. Here the distance travelled by the satellite is equal to the circumference of the satellite. The circumference of the circular orbit. Sorry, the circumference of the circular orbit. The distance travelled by the satellite is equal to the circumference. You know, suppose if the radius is r, then what is the circumference? R 2 pi r. Okay, suppose here the radius is r plus h. So the circumference is 2 pi into r plus h divided by the orbital velocity. Okay, actually the time period is distance by velocity or distance by speed. Okay, here the distance travelled by the satellite is equal to the circumference of the circle. So the circumference of the circle with the radius r plus h is what? 2 pi into r plus h divided by the orbital velocity. Okay, then we can substitute for orbital velocity 2 pi into r plus h. Then you know what is the expression for orbital velocity? We can take root gm divided by r plus h. Root gm divided by r plus h. This thing can be written as 2 pi into square root of this r plus h goes up. So here on r plus h here. And this r plus h when goes inside the root, it becomes r plus h the whole square. Okay, so we have a r plus h the whole square into here on r plus h. So actually it is what r plus h the whole cube divided by gm. Okay, so we got 2 pi into r plus h the whole cube divided by gm. But you know, small g is equal to gm by r square. So instead of gm, we can write gr square. Okay. So which is equal to 2 pi into r plus h the whole cube divided by gr square. Okay. 2 pi into root of r plus h the whole cube divided by gr square. Listen to it. Next we are assuming that if the satellite is very close to earth, so h can be taken as 0. So the time period t is equal to 2 pi into r cube divided by g r square, which is equal to 2 pi into r by g. 2 pi into r by g. And substitute the value of pi, then r and g. We got the value of time period as 84.6 minute. 84.6 minute. That is actually the time period of satellite. 84 point that revolves around the earth. 84.6 minute. Listen to it. This is the expression. Actually, what is the expression for time period of satellite that revolves around the earth? Actually 2 pi into root of r by g. Okay. That is actually time period means the time taken by the satellite to revolve around the earth. The time taken by the satellite to revolve once around the earth, that is actually time period. Next we have to find an expression for time period. Okay, you know, time period equal to distance travelled by the satellite divided by the orbital velocity. Here the distance travelled by the satellite is equal to the circumference of the circle with the radius r plus h. So we can write 2 pi into r plus h divided by orbital velocity VO. Then 2 pi into r plus h divided by, instead of orbital velocity, we can substitute root gm by r plus h. Listen to it. And here, this r plus h that goes up. So square root of r plus h into, and when we take r plus h inside the root, it becomes r plus h the whole square. So r plus h the whole square into r plus h is r plus h the whole cube divided by gm. Okay. Then instead of gm, we can write gr square. So 2 pi root of r plus h the whole cube divided by gr square. Next we are assuming that the satellite that moves very close to the earth's surface, then height h is equal to 0. So t is equal to 2 pi root of r cube divided by gr square. Then r square cancel, and t equal to 2 pi root of r by g. By simplifying this, that is substitute for pi as 3.14 and r earth radius and g acceleration due to gravity 9.8. We got the value of time period of satellite is 84.6 minute. Time period of satellite is 84.6 minute. That is about the time period of satellite. Next about geostationary satellites. Geostationary satellites. Geo means earth, you know. Then stationary means at rest. Actually, these are the satellites which appears to be stationary with respect to earth. Okay, with respect to earth. Geo means earth, stationary means at rest. So, geostationary satellites appears to be stationary, appears to be at rest with respect to earth. Okay, geostationary satellites are those satellites which appears to be stationary with respect to earth. Listen it. Why these satellites appears to be stationary with respect to earth actually? Actually, these satellites always revolve around the earth in the equatorial plane with a time period of 24 hours. Okay, the satellites always revolve around the earth in the equatorial plane with a time period of 24 hours. The time period of earth same time period. Okay, the time period of 24 hours. And the direction of motion of satellite is same as that of Earth. That is from where to where? From west to east. That is why these satellites appears to be stationary. Listen to it. The satellites always revolve around the Earth in the equatorial plane with a time period of 24 hours. And also the direction of motion of the satellite is same as that of Earth. That is from west to east. Okay, that is from west to east. Due to this geostationary satellites appears to be stationary with respect to Earth. Okay, all of you got it? Then what are the uses of these geostationary satellites? Actually, these satellites are used in communicating radio and TV signals throughout the world, all around the world. Geostationary satellites are used to communicating the radio and TV signals or telephone signals throughout the world. Okay, and studying the upper regions of atmosphere. These satellites are used in the study of upper regions of atmosphere. Also, it is used in forecasting weather. Okay, geostationary satellites are used in forecasting weather. And it is also used in the determination of exact shape and dimension of Earth. Exact shape and dimension of Earth. And it is also used in the study of solar radiation and cosmic rays. Actually, these are the uses of geostationary satellites. Geostationary satellites are used in communicating radio, TV and telephone signals all around the world, and it is used in the study of upper regions of atmosphere, then forecasting weather, then determining the exact shape and dimension of Earth, then used in the study of cosmic rays and solar radiations. Okay, that is actually about the geostationary satellites. The next we can see about polar satellites. Okay, polar satellites. That is the satellites which revolves in the polar orbit. That is called the polar satellites. The satellites that revolves in polar orbits is called the polar satellites. The satellites that revolves in polar orbit is called what? Polar satellite. Then what are the uses of these polar satellites? Okay, then polar satellites are used in the weather and environment monitoring. Okay, these satellites are used in weather and the environment monitoring, then used in the spying work for military purposes. Used in the spying work for military purposes. You know, actually the British polar satellite that first detected hole in the ozone layer. This British polar satellite that detected first the hole in the ozone layer. Actually, it is used to study the topography of Mars, Venus and Moon. Okay, that is the uses of polar satellites. Actually, it is used in weather and environment monitoring, then used in the spying work of military purposes. You know, the British polar satellite which detected first the hole in the ozone layer, and it is used in the study of topography of Moon, then Venus and Mars. Okay, that is about what geostationary and polar satellites. Okay. Okay, children, and today's class we have discussed about satellites and about orbital velocity. What is actually orbital velocity? The velocity required by a satellite to put in its orbit around the Earth, that is actually orbital velocity. Okay, also we have learned about we have derived an expression for orbital velocity. Okay, and next we have derived the relation between orbital velocity and escape velocity. That is, escape velocity is root 2 times the orbital velocity. Next we have derived an expression for what the time period of satellite. Okay, next we have learned the geostationary satellites and about the polar satellites and the uses of geostationary and polar satellites. Okay, okay children, that is the end of today's class. Thank you.